our first speaker this afternoon is Denitsa Staicova.
Thank you. So, first, thanks to the organizers for the opportunity to be here in Krakow, because I haven't been here. I'm going to tell you about our results by using the marginalization approach on Baryonic Acoustic Oscillations dataset. And now, the first slide is, in one way, the obligatory slide about the Hubble tension, but I'm going to focus here on something else. So basically, we all know that the Hubble tension stands at about 5 sigma. So this is not new. What is new is DESI's results, which, for example, put it at 3.4 with the BBN prior. Yeah. So this is kind of the new thing. And the other new thing is that we have significant evidence for the WWCDM model. So basically, my talk is going to be focused on two approaches. That one of them is basically directly related to the WWCDM and dark energy models as a whole. So on this plot, what I wanted, on this slide, I wanted to focus on something. So the BO data is known to be degenerate with respect to the matter density and this common factor H0RD. So on this plot from DESI, you could see how this degeneracy looks for the different tracers. So basically here we have the different redshift tracers. And you can see that this degeneracy is kind of deviating for the different redshifts. So if we join them, we get this nice plot that is next to it. This is the DESI's result for omega m and H0RD. So basically, the degeneracy is not something new. And I've made this plot. So now this is an illustration. What it represents is omega matter on the vertical axis and H0 on the horizontal. And these are the different models that DESI has published in their papers. So basically what you see here is the errors and the mean values and also the covariance. So basically these circles, because this is not the contour plot obviously, this is just an ellipse that can illustrate how the covariance looks in the different measurements. And what is interesting is that you can see that all the models that they have published lie on this kind of a line. So basically, even with the different models, we still see this degeneracy. Only it is, if one takes just one model, it is less obvious. But if you plot all of the models, it's very obvious that you have a deeper issue than just taking into account the degeneracy between the sun horizon and H0. So this is why we wanted to find a way to, not to deal with the issue, but to work around the issue, basically to remove H0 and RD from our equations so that we can focus only on the matter density and the dark energy parameters. In this way, and to check what happens in this case, because obviously if we have H0 or the sun horizon, we need to calibrate either with the early or with the late universe, and this will impose automatically this calibration on the final result, and it will make the tension even stronger, or at least as strong as it is. So what we do, basically, this is a way around the issue. So we take the chi-square for our data sets. In this slide here, we have the chi-square for the BO data with covariance. And basically, when you expand this formula here, and you apply the Bayes theorem to it, you can integrate out H0 and RD from our equations, because everywhere they are encountered like this factor here. So if you do the integral from minus infinity to plus infinity, if you start with this chi-square here, you end after the integration with this chi-square here, which does not have H0 and RD inside it. So basically it is free from these parameters. And then we can focus only on the other parameters that we want to examine more in detail and without any calibrations. So basically this chi-square works for both 2D and 3D BO data. I mentioned this because we're going to use it next. And then we can also do similar marginalizations for the other quantities that we have in our data sets. So we have marginalization for the distance modulus. This is a known marginalization over MB and H naught. So basically this is something old that people have done a lot. And also we have the cosmic chronometers marginalization, which is down here, which removes H naught from the equations. So basically what we're left with is just the energy content of the universe. So anything else is removed. And okay, so we have all these marginalizations and we're ready to apply them. So the first application is in the case of dark energy models. This paper is from 2022, so it's a bit older. But the idea here was, and then I think it's relevant to the DESIS result about the WWCDM. So the idea is to apply this marginalization approach to certain dark energy models. In this case, we have CPL, and we have also an alternative to lambda CDM in the form of the phenomenologically emergent dark energy model. So this is this equation here. Yeah, this one here. Okay, this is hard. So this equation here. And in it, what it is important is that we have some kind of transition redshift at which our equation for the cosmological constant changes. So we have this transition, this ZT is found from another equation, so it's not a free parameter, it's not from the MCMC, it is found exactly, so this is not a parameter, but the important thing to mention here is that we recover lambda CDM for theta equals 0. So basically this will be important for the plots afterwards, while the model with theta, with delta, sorry, with delta is the bigger model called generalized emergent dark energy model. So this is the thing about it. And then we move on to the inference. Now, in our paper, we do it for the 3D BAO points and the 2D BAO points, where the 3D are the mixture between the radial and the angular BAO points measurements. And also we have the transversal BAO points, which are 2D and which are just angular measurements. But I'm going to show you here just the 3D plots, because the 2D have a bit bigger errors, and they can be seen in the paper anyway. And in the second part of the talk, I'm going to focus on the transversal BAO points. So basically what we see here, on the top we have, on the top we have just the BAO points. On the bottom we have the BAO plus the supernovae. The supernovae dataset here is the Pantheon dataset. So this, as I said, this is work from 2 years ago. So we didn't have Pantheon plus back then. So you can see that we start with larger than -1 W0. So this is the WWCDM. And then when we add the supernovae, we get this smaller than -1 W0. While for WA, you cannot constrain much. It's very hard to constrain parameter. Then we have WCDM model, which is here. And we observe the same thing. So we start with something larger than -1. And then when we add the supernovae, we get much closer to 1 CDM. And then this is the interesting plot, basically. Okay, maybe. So the plot on the bottom, this is for the GED model. So what you can see is that first with the BAO points, we basically recover 1 CDM. While when we add the supernovae dataset, we go to the left, and this is the PED model. So this is the interesting part, that instead of focusing strictly on lambda CDM, when we add the more precise dataset, we actually sit on the PED model, and the PED model will be seen again later. So first, this is for the matter density, because I really think that the matter density is a parameter that is not paid enough attention to. And you can see how when we have only the BAO points, we start from the left. And when we add the supernovae dataset, we go to the right to higher values of the matter density. So this is one. For the transversal BAO points, the plot looks similar, but just the errors are bigger. And this is why I decided to leave just this one, to make it simpler for everyone. But the result is the same. And this on the top is the Planck value. So basically you can see how some models are quite far from the Planck model, while others are not. So for example, this is for the PED, which I said is going to be mentioned later. So basically you start with a value when we start just with the BO points, you start with the Planck value, and then you go much higher. And the same repeats for the GED model. So basically, this is for the matter density from these results. And then this is the statistical measures that we employ to check the models. And in this case, this is something very interesting. And this is why I have both the 3D and the 2D results. So in this square here is the quadrant where lambda CDM is preferred. So this here is the Bayesian factor, and this is the Kaike criteria on the horizontal axis. So where the square is basically where the models prefer lambda CDM. So you can very clearly see now with the circles. Okay, I didn't change this. So with the circles is the BO data, and with the diamonds is the BO plus supernovae data. So you see on this plot, for example, the circles, meaning the BO data, are somewhere with low preference for lambda CDM, while when you add the supernovae data, you get quite high, where you have very strong preference for lambda CDM. Basically, adding the supernovae data here leads you directly to lambda CDM, except for you can see the PD model standing here very far from preference from lambda CDM, meaning that this model is preferred over lambda CDM definitely. And GED is also somewhere here. And this is lambda CDM with the supernovae data. As I said, WWCDM in this, with these data sets is not doing well because you cannot constrain WA at all. So basically, whatever you do, it's going to not look very good. I haven't tested it with the deci points yet, so I don't know how it's going to look in this case. But anyway, so now you see on the right, you can see the 2D data. And here you can see a much bigger spread over the quadrants. So basically, this is the lambda CDM preference quadrant. And here, it's basically nothing. And when you add the supernovae, you get somewhere here where it's inconclusively positive about lambda CDM. But in the rest of the cases, in the Kaike criteria, you are definitely preferring lambda CDM, while with respect to the Bayesian factor, you are not preferring it. But this is an inconclusive value. So basically, we cannot say for this data set, we don't get conclusive results just like here, because here with the supernovae data, this is actually divided by 4. So actually, the value is somewhere here. So it's very, very preferring lambda CDM. And so the conclusions for this section are that we have different preference for different models from the two different BO data sets. And this is, I think, relevant because even, especially right now with DESI, we see a little bit of argument about between the 3D and the 2D BO points. So on the one hand, you can definitely say that they give different results. This is obvious even just from this plot. Basically, they look very differently just from the statistical measures. So they are different. But on the other hand, you can see that there are there is a much wider spread over the quadrants. So the two data sets definitely give different results. But also, it is very interesting why. So this is the question that nobody has responded to. Why the 3D BO points have such strong preference for lambda CDM, while the others don't have this. Also, most of the results are within the error boxes of SDSS, which are calculated with the full chi-square. So basically, this is a good sign for the approach, meaning that we're not losing too much of a precision because we're ignoring H0 and RD. And also, something interesting is that the PD model is definitely standing out, especially when you add the supernovae data. It just gets even more preferred. So this is an interesting model that maybe is not getting enough attention. And okay, so this is the paper where we published this with David Benisti. And then I'm moving on to the second application. So basically, the second application is more recent. It is in the interacting dark energy models. And this is work that we did with Eleonora Di Valentino and Rafael Nunes and Suprayopan and David Benisti. Yes, okay, I think it's all. So it's an old model that has gotten, so I've cited some of the works here. But basically the idea is what will happen to our model if we allow for energy exchange between the dark energy and dark matter. So we include this interaction function here, which is some kind of parametrization. The parametrization we choose is the standard one written here. And basically, you can get to these equations from different modified gravity theories. But in this concrete case, we don't do that. We just take the phenomenological equations, and we check what will happen if we apply them to the data sets we have. And so this is the final form of which enters into the Friedman equations. Now, the important thing is that here we distinguish two models, Xi-CDM, which is when this is corresponds to lambda CDM, and W-Xi-CDM, which is with W. Okay, so for the data sets we use, this is the calibrated with the Cepheid Pantheon plus, the non-calibrated with the Cepheid Pantheon plus, and just Pantheon for comparison. And we use the transversal BO data sets, so the 2D, and the cosmic chronometers. So first, this is the posterior for the Xi-CDM model because it looks better. And you can clearly see that the three different supernovae data sets give definitely different results. So the Pantheon plus, the pure Pantheon gives a much wider constraints, while the Pantheon plus is much more narrow. But you can also see they are definitely giving different results. And I'm going to discuss this in the next slides. So this is the result for when we impose uniform prior on the matter density, because if you remember, we marginalized over H0 and RD. So basically, they are not in the problem. The only physical parameter is the matter density, and this coupling parameter, Xi. So for uniform prior over the matter density, we get these values for Xi. And here we have two interesting things. So this is the value for the uncalibrated Pantheon plus data set. It sits on lambda CDM, definitely. But for the calibrated data set, we get this very negative value, which is negative within 95% confidence level, so it's very negative. For the other models, we see that, or just for the Pantheon, it is positive value, and it also excludes lambda CDM, but within 95% confidence level, it is recovered. So basically, it's there. And for the other, we have a much bigger value. If we impose the CMB prior here, we see even bigger deviation from lambda CDM. So basically, the uncalibrated with Cepheids value goes much to the left, while for the Pantheon value, it goes much to the right, and everything else goes to the right, meaning positive Xi. And the only thing that recovers lambda CDM is basically the non-calibrated Pantheon plus data set. So the conclusions from this work are basically that we get this very interesting value, which is definitely not compatible with lambda CDM, and it shows an energy flow from dark energy to dark matter. And this can be seen also here. So basically, you see we have much larger value for the matter density than if we had just lambda CDM. So we can see here for the thing that corresponds to lambda CDM, it is much closer to Planck. And basically, for the other models, we don't see such good results. This is for the uniform prior, so this is why the errors are so big. So basically, again, we see different results for the different data sets. And we see that the marginalization procedure has its uses because it allows us to just decouple from the tension directly and not have to deal with any calibrations, and then just to see what happens to the other parameters without it. So this is my talk. Thank you.
And questions?
Okay, I just ask a very simple question. As you use the prior Xi from -1/3 to 1.
Yeah.
So the question is why do you use this prior? Is it related to some speed?
It is related to numerical issues. So basically, if you put this to -1 from 1, the way we were supposed to, you get in the negative part of the interval, you get numerical issues like imaginary stuff, and the code is not working. So you have this areas of this interval where the thing is definitely imaginary. So you cannot work with it, and it's really hard to extend it in this direction. So this is why.
Oh, okay, another question. Do you believe there is interaction between dark matter and dark energy?
Do I believe? I don't know this. I think why not? I mean, in the end, if you have some because before that I worked on some modified theory models, and in them you have an interaction. I mean, it's not stated like interaction between dark matter and dark energy, but you have, for example, if you have scalar fields that interact with each other, this will definitely give you interaction. So here the thing is that this is just the empirical model that we use. This is the parametrization, but we don't know how it is derived. And if you have a model which suggests such interaction, why not? It is possible, why not?
I just think we are working on it, but we don't know it.
No, we don't know it. I'm just saying it's possible.
Thank you.
Okay, thank you.